Good morning, all of you. So today we are going to learn diffraction. Okay, what is that? Diffraction. So first of all, what is this diffraction? Okay, you should know what is the definition of diffraction or what is this process particularly. So let's see. How we can define this diffraction. Can I write like this? That bending of light around edges of an obstacle. What is that? Bending of light around edges of an obstacle means when any obstacle is coming in the path of that light, then light will bend at the edges, sharp edges. Okay, that is what your diffraction is. What is that? Bending of light around edges of an obstacle. Around edges of an obstacle. Or you can say like this also, because if suppose you are having a sharp knife edge and you are incidenting light on that edge, then how light bends at that edges, that is what nothing but diffraction. So can I write like this? A spreading of light waves spreading of light waves as they pass through narrow opening or move past an obstacle. Okay, this is what diffraction means. Just you can say spreading of light waves. Okay, spreading of light waves as they pass through narrow opening. Next point. See here now, what is the next point I'm going to write? As wavelength of visible light ranges from 4,000 angstrom to 8,000 angstrom. Since wavelengths are very small, as compared with the sizes of ordinary object or apertures. Aperture means what? Area through which light enters. Okay. Apertures, diffraction of light diffraction of light is not easily noticed. Is not easily noticed. One diagram I am giving you. You see here. Now this is an opening. Okay. A narrow opening. And now light is coming like this. Okay. And when it is crossing this narrow opening, then this light is going to spread like this. Okay. If you do not draw this also, okay. But light is going to spread like this. Okay. When it is passing past an object, obstacle or narrow openings, we can say. Right? So now how many types of diffractions are there? Okay. First you understood this. What is diffraction? Now types of diffraction. Right? Okay. So types of diffraction, we can see here. There are two types. First one is Fraunhofer, another one is Fresnel. First one is Fraunhofer, another one is Fresnel. In Fraunhofer diffraction, when it takes place, when parallel rays are incident on it, then it is Fraunhofer diffraction. Means whatever diffraction is taking place, that is if it is because of the rays which are parallel incident on the slit or knife edges, or we can say on an obstacle, then that is Fraunhofer diffraction. You can see in the diagram here, you see this is a narrow slit, we can say, and these rays are parallel which are incident on this, and then this is diffraction which we are getting. Here also you can see this is a source, and here I have kept one convex lens, and then after this these rays are parallel, and because of this whatever diffraction is there, that is what it is below Fraunhofer diffraction. Next one is Fresnel diffraction. So this takes place at a narrow slit when non-parallel rays are incident on it. So in this case, you will get non-parallel rays. So you can see these are the not parallel rays, which are like this as shown in diagram. And if because of this, whatever diffraction you are getting, that comes under the category of Fresnel diffraction. Understand? So draw these diagrams, note down, right? So if we will see the pattern which we are getting on the screen, so pattern will be like this. So this is your slit, and this is the screen, and on this you are getting this pattern. So if you will see at the center, you will get the big spot at the center, and as you are going upwards or downwards from this bright spot, its intensity will go on decreasing. So if you will see the graph, that is I versus path difference here, then you will get something like this graph. Okay, this side also you will get something like this. Okay. So as you are going this side and that side, your intensity will go on decreasing. So here it will get maximum intensity spot, then intensity will go on decreasing this side as well as this side also. I will show you this pattern in the lab. Okay, right? So let's move ahead. Note down this, you can draw this diagram. This is diffraction pattern which we are obtaining or which we are getting on the screen. Right, next. Diffraction at single slit. Okay, what we are going to do? Diffraction at single slit. Means in this we are going to take one single slit and we are going to incident light, and then how we are getting that we are going to learn here. Right, let's draw the diagram first. Suppose now this is a slit here, and assume that some rays are going parallel like this. When they are going to fall on this at this screen, we will get one bright spot because all these rays will converge here like this. And here theta is equal to what? 0, because all the rays are parallel, and this point is A, this point is B, and this point is C. Okay, from which these rays are going exactly parallel, A, B, C. And let's assume that this slit width is small d. What is the slit width? Small d. Here it is, small d. And this point is point O, and this one is what? Screen. As usual, the distance between this screen and this slit is how much? Capital D. How much the distance is? Capital D. Right. So this diffraction pattern on the screen is formed because of superposition of secondary wavelets. So diffraction pattern on the screen is formed due to superposition of secondary wavelets. superposition of secondary wavelengths. At point O, what happens? All waves will arrive in a same phase, and that's why there it is a bright fringe. Yes or not? When all waves construct interference, then bright fringe is getting formed. So at point O, waves arrive in a phase. Waves arrive in the same phase or just in phase. Hence, there is what? Central bright fringe. Central bright fringe. Right? This is what? Central bright fringe. Now, if you want to find positions of secondary minima and all, how we will find? Okay, positions of secondary minima and positions of secondary maxima for this. Let's see ahead. On the next page, I'm going to draw the diagram. First, note down this, pause the video and note down these 2-3 points and draw this diagram. Okay, so let's see how it is. That is position of secondary minima. Positions of secondary minima. Positions of secondary minima. Again, I'm taking this slit. Okay, and these are the rays which are incident parallel. And now here is a screen. You can see this is a screen. As usual, this is your bright spot, midpoint. And now I'm taking point P1 here because these rays are going to reach here also. And now what I'm doing, I'm drawing one perpendicular. With white light, I will do this for white color. I'm drawing one perpendicular here. And this one, I will denote with the dotted lines. Can you see? This is a perpendicular here, and I am giving that point as a name as a n point, and this is lambda wavelength. This point is A, this point is B, and this point is N. And let us suppose this angle is theta 1. Angle is what? Theta N. Now here P1 is first secondary minimum. P1 is what? First secondary minimum. And in triangle ABN, sine of theta 1 is equal to an by AB. Yes or not? You can see here. AN by AB. Opposite by hypotenuse. This is AN by AB. But this AN is what? AN is D. Yes or not? This is how much? D. Already in the previous diagram also I shown you. This slit width, how much we have taken? It we have taken as a small d. So this is D. So therefore this is equal to AN is D divided by AB is what? AB is what? AN is lambda, na? AB is D. Okay, 1 minute. AN is what here? AN is lambda and AB is D. Again. Okay, so AN is lambda and this is D. And therefore what we are getting now? Lambda is equal to D sine theta 1. See in the diagram. Right? Lambda is equal to what we got? D sine theta 1. Now, path difference for minima is what here? Path difference in this case. Path difference is equal to n lambda, and therefore d sine theta n is equal to n lambda. This is for first one. If suppose nth maximum you want or nth minimum you want, then d sine theta n is equal to n lambda, and therefore sine of theta n is equal to n lambda by d, where n is equal to 1, 2, 3 and so on. This formula is important for minima. Next one, similarly, positions of secondary maxima. Positions of secondary maxima. So in this case, for maxima, what we are getting? That is 3 lambda by 2 is equal to d sine theta 1 dash. Next 5 lambda by 2 is equal to d sine theta 2 dash and so on. Therefore d sine theta n is equal to 2n plus 1 lambda by 2. 2n plus 1 lambda by 2. And therefore, if I want sine theta n for this maxima, then it is equal to 2 into n plus 1 lambda by 2 into d, where n is equal to 1, 2, 3 and so on. So if they are asking in a problem this type of question, you should be able to use this formula. Okay, so note down this, draw the diagram wherever it is necessary, right? So let's stop here for today. Bye.